The universe began in total darkness. For millions of years, it was a silent, black expanse of primordial gas. Then, something extraordinary happened. A mysterious event called the Cosmic Reionization Era tore through the cosmos, fundamentally reshaping everything. This pivotal epoch transformed that ancient darkness into the brilliant, star-filled universe we know. Yet it remains one of the greatest unsolved puzzles in all of science. By the end of this journey, you will understand the 25 profound mysteries that define this cosmic transformation. We will uncover what triggered the very first starlight and confront the bizarre signals that defy our current laws of physics. What do you think it took to illuminate the entire cosmos? That initial spark of starlight remains one of the most sought-after events in cosmic history. For millions of years, the universe was a dark, neutral sea of hydrogen gas, and then something, somewhere, switched on for the very first time. But what was that first light? What cosmic object had the power to ignite the entire cosmos? Scientists call this the mystery of the first light, and the suspects are as fascinating as they are elusive. The prime candidates are unimaginably ancient stars, known as population 3 stars. These were not like the stars we see today. They were behemoths, hundreds of times more massive than our own sun, burning ferociously hot and dying young in spectacular supernovae. Their intense ultraviolet radiation would have been the perfect tool to start stripping electrons from the surrounding hydrogen, beginning the process of reionization. Another potential culprit is the early quasar, a supermassive black hole at the heart of a nascent galaxy, greedily consuming matter and shooting out unimaginably powerful jets of energy. These cosmic lighthouses could have flooded vast regions of space with ionizing radiation. So why is pinpointing the true source so difficult? The very first stars and quasars are incredibly faint to our telescopes, lost in the fog of time. We are essentially looking for the glow of a single match from across an entire continent, shrouded in 13 billion years of history. The question is not just what turned the lights on, but whether it was a sudden, brilliant flash or a slow, dawning sunrise across the cosmos. This leads us directly to the next great puzzle, the timeline of this cosmic dawn. How quickly did this illumination actually spread? Pinpointing that first spark of light is just the beginning. The true controversy lies in figuring out the entire lifespan of this cosmic dawn. Did reionization happen in a sudden, explosive burst, or was it a slow, drawn-out process that unfolded over an immense stretch of time? This is the mystery of the timeline, and it is a debate fueled by conflicting evidence from the deepest reaches of space. One of our most powerful tools is the cosmic microwave background, the ancient afterglow of the Big Bang itself. This faint light carries an imprint, a memory of when the universe was reionized. Data from this primordial echo suggests reionization was a relatively late and rapid event, beginning around when the universe was 400 million years old and concluding by the time it reached 1 billion years. Yet, when we look at some of the most distant quasars, their light tells a different story. We see hints that vast patches of the universe might have already been transparent, with the hydrogen gas cleared away much earlier than the cosmic microwave background implies. So which cosmic clock is correct? The answer is vital. If reionization happened quickly, it implies a universe dominated by incredibly powerful, concentrated sources of energy, like those brilliant first stars. A slower, more gradual timeline suggests that smaller, fainter galaxies did most of the heavy lifting over billions of years. The entire story of how structure formed in our universe, from the first stars to the great cosmic web, hinges on resolving this chronological conflict. And this uncertainty about timing leads us directly to another, even more fundamental question. What was the actual environment like during this era? What did the cosmos look like as it was being transformed? The very fabric of space was changing. But what cosmic engines were powerful enough to drive this transformation? While we often picture brilliant quasars and massive stars, the true workhorses of reionization might have been far more humble. Scattered across the early cosmos were countless small, faint galaxies, the cosmic toddlers of the universe. These were not the grand spirals we see today, but rather fragile, clumpy collections of gas and the first few generations of stars. Their individual light was feeble, a mere candle compared to the blaze of a quasar. Yet, their sheer numbers present a compelling possibility. Could an army of cosmic fireflies have lit up the entire universe? The math is tantalizing. If enough of these small galaxies existed, their combined output of ultraviolet light could, in theory, have provided the billions upon billions of ionizing photons needed to clear the cosmic fog. But there is a critical catch. These early galaxies were swaddled in thick cocoons of their own gas. When a massive star inside one of these galaxies produced its powerful UV radiation, that light had to fight its way out. It risked being absorbed by the very hydrogen gas it was meant to ionize, just inches from its source. This creates a dramatic cosmic conflict. Was the radiation from these small galaxies efficient, escaping freely to travel great distances and ionize the vast intergalactic medium? Or was it largely trapped, making these galaxies far less effective than their numbers suggest? The answer determines the entire character of the reionization era. If small galaxies were efficient, then the universe was illuminated by a diffuse, widespread glow. If they were inefficient, then we must look back to those rare, monstrously powerful sources to explain the great cosmic thaw. This uncertainty forces us to look even closer at these infant galaxies, to ask what was happening within their chaotic hearts. What internal battles between light and darkness ultimately shaped the fate of the cosmos? Deep within the hearts of those early galaxies, a different kind of cosmic monster was awakening. Quasars are the most violently energetic objects in the universe, powered by supermassive black holes feasting on colossal amounts of gas. As matter spirals into the gravitational abyss, it heats to millions of degrees, blazing with a light that can outshine an entire galaxy. Imagine a single beacon so powerful it could punch a hole through the cosmic fog for millions of light years around it. This raw, focused power makes quasars a prime suspect for driving reionization. Their intense jets of radiation would have been ruthlessly efficient at stripping electrons from hydrogen, potentially carving out vast, transparent bubbles in the neutral cosmos long before other sources could. The argument for quasars as the dominant force is one of sheer, concentrated might. A single, brilliant quasar could accomplish what would take millions of those smaller, faint galaxies. But this argument runs into a formidable problem, a problem of cosmic statistics. Quasars were incredibly rare, especially in the early universe. For every quasar blazing away, there were immense, dark voids where no such cosmic lighthouse existed. More critically, their lives were spectacularly short. A quasar's brilliant flash is a fleeting event in cosmic time, a brief frenzy of feeding that may last only a few million years before the fuel supply dwindles and the light fades. Could these rare, short-lived flashes truly have been responsible for systematically ionizing the entire universe? The counter-argument suggests they were more like dramatic fireworks in a long, dark night. They undoubtedly lit up their own local neighborhoods, creating isolated pockets of clarity, but they may have been too few and too brief to orchestrate the global transformation on their own. The debate hinges on a cosmic census we do not yet have. How many of these early quasars actually existed? Were they just the dazzling exceptions, or were they common enough to have been the primary architects of the reionization era? The answer lies shrouded in the deepest reaches of time, forcing us to question whether the universe was reshaped by a few brilliant titans, or by the collective effort of an uncountable number of tiny sparks. But even if we count every single star in every single galaxy, we immediately hit another, far more subtle wall. The true power of these cosmic engines was not just the light they produced, but the light that actually got out. This is the deeply frustrating mystery of the escape fraction. Think of an early galaxy not as a clear pane of glass, but as a dense, swirling fog bank. Inside, brilliant new stars are born, flooding their immediate surroundings with the very ultraviolet light needed to ionize hydrogen, but that light does not travel far. It is almost instantly absorbed by the thick clouds of primordial gas and dust from which the star itself just formed. The star's own nursery becomes its prison, trapping its most potent radiation. The escape fraction is simply the tiny, crucial percentage of these ionizing photons that actually manages to fight its way through the galactic fog and escape into intergalactic space. It is the difference between a light bulb shining brightly in a sealed room and one whose light escapes through a window to illuminate the dark street outside. For reionization to work, this escape fraction could not be zero. A significant amount of light had to get out, but just how much? This single, elusive number is one of the most critical and most debated values in all of cosmology. If the escape fraction was high, say 20 or 30%, then even small, faint galaxies could have provided more than enough radiation to reionize the cosmos. But if it was very low, just 1 or 2%, then our entire model falls apart. We would be left with a universe that should still be dark and neutral, a cosmic crime scene where the required energy is missing. The problem is that measuring this value directly is nearly impossible. We are trying to observe the faint, specific glow of escaping radiation from galaxies that are already at the very edge of our observational limits. It is like trying to measure the exact amount of light filtering through the stained glass windows of a distant cathedral, while you are standing miles away in a thick fog. Our telescopes struggle to separate the escaping ionizing light from the galaxy's much brighter non-ionizing light, and from the faint glow of our own atmosphere. So we are left with a gigantic question mark at the very heart of our calculations. Without knowing this one number, we cannot know if the galaxies we see were powerful enough to do the job, or if we are missing something fundamental about the early universe. This uncertainty forces us to look beyond the light itself and into the very shadows it cast. How can we map the darkness that remained? Even the most powerful light can be stopped by a shadow. The success of reionization did not depend solely on the brilliance of the first stars and galaxies, but on the very substance they were trying to penetrate. We are faced with the puzzle of the hydrogen itself. How was this primordial gas distributed throughout the cosmos? Was it a uniform, thin mist or a thick, lumpy fog? The answer to this question, a property scientists call clumpiness, determines whether reionization was a swift and decisive victory for light, or a long, grinding cosmic war. Imagine you are trying to dry a vast, sopping wet sponge. If the sponge is perfectly uniform, the water evaporates quickly and evenly. But if the sponge is full of dense, tightly packed clumps, those pockets of moisture remain stubbornly wet long after the rest has dried. The neutral hydrogen gas of the early universe was that sponge. If the gas was smooth, then the first ultraviolet radiation would have swept through it effortlessly, ionizing hydrogen atoms in a clean, progressive wave. Reionization would have been a relatively fast and straightforward process, but if the gas was highly clumpy, the story changes dramatically. In that scenario, the radiation would have encountered a chaotic landscape. It would have easily ionized the low-density valleys between the clumps, but then it would have slammed into these dense, stubborn knots of hydrogen. To break apart these knots would have required a far more intense and sustained assault. the process would have become patchy and inefficient, with light slowly eroding the clumps from the outside in, creating a complex, Swiss cheese-like structure in the intergalactic medium. The entire era would have been prolonged, perhaps by hundreds of millions of years. So which was it? Our best clues come from sophisticated computer simulations of the early universe. These models suggest that the gravitational pull of dark matter, the invisible scaffold of the cosmos, would have naturally caused the hydrogen to clump together. This points toward a slow and difficult reionization. However, when we look at the light from the most distant quasars, we see a different hint. Their light passes through the ancient hydrogen, and by analyzing how that light is absorbed, we can get a fossil record of the gas's distribution. Some of this data suggests the gas might have been smoother than our simulations predict. We are left with a fundamental disagreement. Did reionization carve its way through a universe of stubborn, dense obstacles, or did it flow freely through a more welcoming and even landscape? The true texture of the early cosmos remains one of its most deeply hidden secrets, a mystery that dictates not only how long the process took, but how the first structures grew within that evolving sea of light and matter. This cosmic war between light and shadow left permanent scars across the universe, scars we can still find today in our own cosmic backyard. The Milky Way is surrounded by a swarm of small, faint satellite galaxies, but there is a profound problem. There are far, far fewer of them than our best theories of dark matter predict. Billions of years ago, the early universe should have been teeming with countless small clumps of dark matter, each one a potential seed for a tiny galaxy. So where did they all go? This is the mystery of the missing satellites, and its origins may lie directly in the fires of the Reionization era. Imagine those first galaxies beginning to blaze, flooding the cosmos with fierce ultraviolet radiation. This was not a gentle dawn. For the very smallest dark matter halos, the ones barely massive enough to hold onto their own gas, this radiation was an apocalypse. The intense heat from that primordial starlight would have boiled away their fragile hydrogen clouds, stripping them of the very fuel needed to form stars. These tiny halos were sterilized, left as dark, starless ghosts orbiting the larger galaxies. They are still out there, made of pure dark matter, but because they never lit up with stars, they are completely invisible to our telescopes. The Reionization era may have been the great filter that decided which cosmic seeds would blossom into galaxies and which would remain forever dark. This explains why we see fewer small galaxies than we expect, but it also raises a startling new question. If this theory is correct, then the vast majority of the Milky Way satellites are not just faint, they are utterly black, detectable only by their subtle gravitational tug. So the very event that illuminated the cosmos may have also created a hidden, dark population of failed galaxies, forever orbiting in the shadows of their more successful cousins. This invisible architecture forces us to reconsider everything we thought we knew about the cosmos, leading us to an even deeper enigma: what other hidden forces were at play, sculpting the universe from behind the scenes. That fierce ultraviolet radiation did more than just strip electrons from atoms. It also fundamentally changed the energy of the cosmos itself. We now face the thermal mystery of the intergalactic medium. What happened to the temperature of the vast spaces between galaxies as the universe was being reborn in light? When a high-energy ultraviolet photon smashes into a neutral hydrogen atom, it does not just free the electron. That liberated electron carries away a significant amount of excess energy, like a spring suddenly released. This energy translates directly into heat, causing the gas to warm dramatically. So, as reionization progressed, the entire intergalactic medium was not just being cleared, it was being cooked. The critical question is whether this was a gentle, steady warming or a violent, explosive heating event. The answer is written into the fossil record of the gas itself, and it tells us exactly what kind of sources were doing the ionizing. Imagine two different scenarios. In the first, reionization is driven by those massive, ferociously hot population 3 stars. Their photons are incredibly energetic, each collision with hydrogen delivering a powerful thermal punch. This would have superheated the intergalactic medium to temperatures soaring past 100,000 degrees. It would have been a sudden, searing flash across the cosmos. Now, consider the alternative. If reionization was instead the work of smaller, more numerous galaxies with cooler stars, the process would have been far more gradual. The photons would have had lower energy, warming the gas to a much more moderate 20 or 30,000 degrees, like a slow simmer rather than a roaring inferno. By measuring the ancient temperature of the intergalactic gas, we can effectively read the signature of the ionizing sources, billions of years after they faded away. So, what does the evidence say? This is where the puzzle deepens. When astronomers study the absorption lines in the light of distant quasars, they are analyzing a cosmic thermometer. The way the gas absorbs light reveals its temperature and density. Current data presents a confusing picture. It suggests that after reionization ended, the intergalactic medium was actually quite warm, but not as blisteringly hot as the massive star scenario would predict. It is as if we found evidence of a great fire, but the ashes are not as hot as we expected them to be. This thermal mismatch is a major unsolved problem. It implies that our understanding of the ionizing sources is incomplete. Perhaps the first stars were not quite as monstrous as we think, or maybe the process was so patchy and drawn out that the gas had time to cool in between heating events. Our current telescopes are straining at their limits to make these delicate measurements, but the next generation of observatories will peer back with unprecedented clarity, seeking the true thermal history of the universe. This record of cosmic temperature is a direct echo of the engines that forged our transparent cosmos, and its mystery forces us to question the very nature of the first starlight. The ancient light from a quasar is a cosmic time capsule, carrying secrets from its billion-year journey. As this light travels toward us, it passes through countless clouds of hydrogen gas, each one leaving a unique fingerprint on the light spectrum. These fingerprints are called absorption lines, and when scientists look at the light from a distant quasar, they do not see just 1 or 2 lines, they see a forest. The Lyman-alpha forest is a breathtakingly dense thicket of thousands upon thousands of these dark lines, each one representing a single cloud of hydrogen the light has encountered. This forest is our most detailed fossil record of the intergalactic medium, a direct snapshot of the universe's structure during and after the reionization era. Decoding this forest is like trying to read the diary of the cosmos, but one where every single entry is written on top of the one before it. The central mystery is one of untangling time itself. The absorption lines from clouds that existed at the very dawn of time during reionization are superimposed with lines from clouds that formed much later. A single spectrum contains a chaotic pile-up of signals from every cosmic epoch the light has passed through. How can we possibly separate the ancient whispers from the more recent chatter? The key lies in looking at the very deepest, most distant quasars. Their light has traveled the farthest, and the part of their spectrum that corresponds to the reionization era is shifted into a specific, predictable range. But even then, the task is monstrously complex. A single line in the forest could be from a small, dense knot of neutral hydrogen that survived the reionization process, or it could be from a vast, diffuse cloud that formed long after the universe was transparent. Distinguishing between them requires incredibly precise measurements and sophisticated computer models that can simulate the entire history of cosmic structure. We are essentially trying to reconstruct the climate of the ancient Earth from a single ice core that has been melted and refrozen 1,000 times. The prize for solving this puzzle is immense. If we can learn to read the Lyman-alpha forest correctly, we could map the exact timeline of reionization. We could see the precise moment when the number of neutral hydrogen clouds began to plummet as the cosmic fog was burned away. We could measure the temperature and clumpiness of the gas with unparalleled detail, finally answering whether it was a smooth sea or a field of stubborn knots. This forest of shadows holds the truth about how the universe transitioned from a simple, dark place into the complex, structured cosmos we inhabit today. Yet this intricate fossil record points toward an even more fundamental question. What was the source of the very first light that began to carve these patterns into the cosmos? The cosmic forest of hydrogen shadows tells us the great ionization was underway, but it does not reveal the final act. How did this epic era actually conclude? The end of reionization presents a profound puzzle. Did the universe simply reach a tipping point where the growing bubbles of ionized gas finally touched and merged, filling every last corridor of space with light? Or was there a specific, dramatic event that catalyzed the final, rapid phase of clearing? One compelling theory suggests it was a simple matter of cosmic geometry. In the beginning, isolated bubbles of ionized hydrogen, each carved out by a bright galaxy or quasar, were like lit candles in an immense, dark cavern. For millions of years, these bubbles grew slowly, their edges pushing against the stubborn neutral gas. Then, a critical moment arrived. The bubbles began to overlap, their boundaries connecting. Suddenly, a photon of ultraviolet light could travel from one end of the cosmos to the other without ever hitting a neutral atom, because it could now hop from one ionized bubble to the next. This created a runaway effect, a final, swift ionization of the last remaining neutral pockets, which were now surrounded and defenseless. It was less a battle and more a cosmic tide, finally washing over the last few grains of sand. Yet another theory proposes a more fundamental shift. Perhaps the universe's own expansion finally diluted the remaining hydrogen gas to such a low density that it became trivial for the ever-present radiation to keep it ionized. The war was over not because the light grew stronger, but because the enemy simply thinned out and faded away. The evidence we desperately need to distinguish between these scenarios is maddeningly elusive. We require a snapshot of the universe at the very moment of this transition, a map showing the exact distribution of the last neutral hydrogen strongholds. Our current telescopes can only see the aftermath, a universe already fully transparent. The next generation of observatories, like the James Webb Space Telescope, is searching for this final chapter by looking for the faint, telltale glow of the last neutral hydrogen clouds as they were being evaporated. Finding that signal would be like discovering the final page of a lost historical manuscript, revealing whether the cosmic dawn ended with a quiet sigh or a brilliant, final flash. That final, brilliant flash of reionization may have had a hidden accomplice, a force operating entirely in the shadows. While stars and quasars provided the visible light, the invisible hand of dark matter might have been quietly assisting in the cosmic transformation. This leads us to a deeply speculative but thrilling possibility. Could dark matter itself have been a source of the energy that helped clear the cosmic fog? The standard model of cosmology treats dark matter as completely passive, a ghostly scaffolding that guides the growth of galaxies through its gravity alone. It does not emit, absorb, or reflect light. But what if certain types of dark matter were not quite so inert? Some theoretical physicists propose that dark matter particles could possess a rare but potent property, the ability to annihilate with one another. When two of these hypothetical particles collide, they would not simply bounce apart. They would vanish in a flash of pure energy, converting their entire mass into other particles, including gamma rays and fast-moving electrons. Now, imagine this process occurring on a cosmic scale, throughout the vast halos of dark matter that enveloped every early galaxy. This annihilation would provide a steady, pervasive background glow of high-energy radiation, a form of invisible starlight emanating from the dark universe itself. This energy would have acted as a constant, low-level heat source for the primordial hydrogen gas. It would not have been as dramatic as the blast from a supernova, but it would have been everywhere, a gentle, universal warming that could have preheated the gas, making it easier for the ultraviolet light from the first stars to finish the job of ionization. Think of it like trying to melt a block of ice. You could focus a blowtorch on one spot, which is like the intense light from a quasar, or you could place the entire block in a warm room, making it soft and malleable, so that even a modest amount of direct heat can quickly turn it to water. The annihilating dark matter would have been that warm room for the entire universe, subtly shifting the balance in light's favor. Of course, this remains a fringe idea, far from the scientific mainstream. There is no direct evidence that dark matter particles can annihilate, and if they do, the rate might be far too slow to have had any meaningful impact. Yet, the mere possibility is profoundly alluring. It suggests that the story of cosmic reionization, the story of how our universe became bright and transparent, might be a tale of two universes, the visible and the dark, working in a strange, unseen concert to forge the cosmos we call home. This invisible partnership forces us to confront an even more fundamental question about the nature of the first structures themselves. If dark matter was so crucial, how did it first begin to clump together to create the seeds for everything that followed? Our search for the cosmic engines of reionization might be missing an entire army of invisible soldiers. We have looked to brilliant quasars and faint, early galaxies, but what if a vast, hidden population of cosmic objects did a significant part of the work, objects our telescopes simply cannot see? These are the theorized dark galaxies, the silent partners of the reionization era. Imagine a galaxy that formed in the early universe, rich with gas, but for some reason, it failed to light up with stars in any significant way. Perhaps its gas was too turbulent, or it was missing a key gravitational nudge to begin star formation. This galaxy would be brimming with the raw fuel for creation, yet it would remain almost completely dark, a ghostly ship adrift in the cosmic sea. Now consider a different scenario, a galaxy that did form a first generation of stars, but those stars were immediately shrouded in a thick, impenetrable blanket of cosmic dust. This dust, forged in the hearts of those early stars, would absorb nearly all the visible light, re-radiating it as a faint, long wavelength glow that is incredibly difficult to detect across billions of years. To our most powerful observatories, both of these galaxies would be virtually invisible. They would not show up in our deep field images that hunt for the faint glimmer of starlight. They are the cosmic missing matter, the ones that got away. So why would we think these phantoms had any role in reionization? The answer lies in a subtle but profound possibility. Even a dark galaxy, if it managed to form just a few massive stars, could be a potent source of ionizing radiation. If those stars were born in a specific configuration, or if the galactic gas was arranged in just the right way, the fierce ultraviolet light might actually escape more easily than in a brighter, more chaotic galaxy. A dark galaxy would have less gas and dust to obstruct the light's path out. This creates a paradoxical idea. The most important contributors to lighting up the cosmos might not have been the galaxies we can see, but rather the countless billions we cannot. They could have been the universe's stealth bombers, delivering their payloads of ionizing photons without ever revealing their position. The problem, of course, is proving they existed at all. Finding them is one of the greatest observational challenges in modern astronomy. It requires looking not for starlight, but for the faint, indirect signatures of their presence, such as the subtle glow of hydrogen gas being excited by an unseen source of energy. If we cannot find this hidden population, our census of the reionization workforce is fundamentally incomplete, forcing us to wonder if the universe used a shadow army to win its war against darkness. Just as the cosmic fog of hydrogen was finally clearing, a second, more subtle transformation began. The universe was not finished being forged. This is the mystery of helium reionization, the forgotten second act in the story of our cosmic dawn. For millions of years after hydrogen was ionized, the vast majority of helium atoms in the intergalactic medium still held onto their electrons. Helium is a tougher atom, with a stronger grip on its particles. It requires photons with even higher energy, far into the extreme ultraviolet range, to tear them apart. The first stars and small galaxies simply did not produce enough of this brutal radiation to do the job. So the universe had to wait for a more powerful engine to emerge. That engine was almost certainly the quasar. As supermassive black holes in the hearts of galaxies reached their peak of activity, their accretion disks blazed with a ferocious intensity, emitting the precise type of high-energy photons needed to assault the stubborn helium. This second wave of ionization likely began when the universe was around 1 to 2 billion years old, long after the hydrogen had been cleared, and it may have dragged on for billions of years more. The timeline is incredibly murky. Was it a swift, unified event, or a drawn-out, chaotic process that varied from one region of space to another? The impact of this second reionization was profound. When a helium atom is ionized, the released electron carries away even more energy than it did from hydrogen. This means the helium reionization would have reheated the intergalactic medium, potentially raising its temperature to millions of degrees. This cosmic reheating would have fundamentally altered the conditions for galaxy formation, affecting how gas could flow into developing galaxies and cool to form new stars. It placed a second thermal fingerprint on the universe, a signature we are still trying to decode in the faint light of distant quasars. The great uncertainty is that quasars were sporadic. Their distribution across space and time was patchy, meaning the ionization of helium could not have been a smooth, uniform wave. It must have been a messy, fragmented process, creating a new, complex pattern of hot and cold bubbles in the intergalactic gas. The second act adds a deep layer of complexity to our cosmic narrative, forcing us to see reionization not as one single event, but as a multi-stage rebirth, where the universe was sculpted and resculpted by different forces across billions of years. This cosmic cycle of creation and destruction was governed by a delicate, universal balance. The very radiation that cleared the cosmic fog also held the power to choke off the future of star formation, creating a self-regulating feedback loop that dictated the pace of cosmic evolution. On one hand, the fierce ultraviolet light from massive stars was a vital catalyst. As it streamed out into the cosmos, it ionized vast regions of hydrogen gas, but that was not its only effect. This intense radiation also heated the gas to extremely high temperatures. Hot gas resists collapsing under its own gravity, so within the immense ionized bubbles, the process of forming new stars was dramatically slowed, as the raw material for building them was kept too hot and energetic to clump together. The very engines of light were effectively turning off their own fuel supply in the regions they had already conquered. Yet, at the very edges of these expanding bubbles, a different story unfolded. Here, the radiation and heat from the interior met the cold, dense wall of the remaining neutral hydrogen. This collision created a powerful shockwave, compressing the gas at the boundary. This sudden compression could trigger a burst of new star formation, like a cosmic snowplow piling up a bank of snow. So, the same event that suppressed star formation in one area could actively promote it in another, pushing the frontier of cosmic dawn ever outward. This feedback loop created a natural thermostat for the universe. If star formation became too vigorous, the resulting radiation would quickly heat and disperse the surrounding gas, putting a brake on further activity. If things became too quiet, the gas would eventually cool and collapse, reigniting the cycle. The entire reionization era was likely a series of these pulsing, rhythmic bursts, a cosmic symphony of creation and destruction, whose echoes determined the final architecture of the universe. Understanding this intricate dance is one of the greatest challenges in modern cosmology, because it forces us to ask a deeper question: how could such a chaotic and violent process lead to the stable, structured cosmos we see today? This distinction between the cosmic dawn and the epoch of reionization is one of the most fundamental yet misunderstood concepts in this entire story. The cosmic dawn is the moment the very first star flickered on in the endless dark. It is the birth of a single, lonely candle in an unimaginably vast cavern. For the first time since the Big Bang, something other than the primordial fireball was generating light. The epoch of reionization, however, is not that first spark. It is the great fire that followed. It is the story of how that single candle ignited others, and those ignited more, until the entire cavern was ablaze with light, permanently transforming its very atmosphere. So why the immense delay? Why did hundreds of millions of years pass between the lighting of that first candle and the moment the cosmic fire truly took hold? This gap is one of the central mysteries of our cosmic history. The first stars were likely colossal and brilliant, but they were also incredibly isolated. They were scattered like distant campfires across an entire continent of darkness. Their light could only ionize a small bubble of gas around them before the radiation faded. And when these short-lived giants died in spectacular supernova, their light was extinguished, allowing the neutral gas to perhaps rush back in. The universe was stuck in a frustrating cycle of flickering. Light would appear, push back the darkness for a short while, and then vanish, letting the shadows reclaim their territory. The permanent change, the true epoch of reionization, could only begin when the universe reached a critical threshold. It required not just the existence of stars, but a sufficient density of them. It needed galaxies to form, acting as stable, long-lasting factories for producing new generations of stars. Only when these factories were numerous enough and their ionizing radiation could escape efficiently did the isolated bubbles begin to overlap and merge. This created a network of ionized highways, allowing light to travel vast distances without being absorbed. The delay, then, was the time it took for the cosmos to build its infrastructure. It was the slow, gradual process of gravity pulling together the first galaxies, amassing enough fuel to sustain a continuous, widespread blaze. Think of it like trying to light a damp log with a single match. You might scorch the surface, but the match burns out before the log truly catches fire. You need to gather enough dry kindling first, building a sustained heat that can eventually ignite the log itself. The cosmic dawn was that first, fleeting match strike. The epoch of reionization was the patient gathering of kindling until the entire log was finally, permanently set ablaze. This hidden battle between flickering light and persistent darkness forces us to ask what finally tipped the scales. What was the final, crucial ingredient that allowed the fire to spread and forever change the state of the universe? That final, crucial ingredient might be hiding in a whisper of radio static from the dawn of time, tuned to a specific, almost imperceptible frequency. Our most powerful radio telescopes are now listening for the one signal that could turn our collection of fossilized snapshots into a full motion picture of the reionization era. This is the hunt for the 21-centimeter line, the direct voice of the ancient hydrogen gas itself. Every neutral hydrogen atom in the early universe was a tiny radio transmitter. Its single electron and proton each possess a property called spin, and when those spins flip from being aligned to being opposed, the atom releases a photon of light with a very specific wavelength, 21 centimeters. This is a fantastically weak signal from a single atom, but when you multiply it by the septillions upon septillions of atoms filling the entire cosmos, it creates a faint, all-encompassing radio glow. By tuning our instruments to the right frequency, we should be able to map the distribution of neutral hydrogen throughout the reionization era, watching in real time across billions of years as the great ionized bubbles grow and merge. This signal would be our ultimate time machine, allowing us to produce a frame-by-frame movie of the cosmic dawn. The challenge is that this primordial signal is not just faint, it is buried under an avalanche of noise. The first and greatest obstacle is the sheer expansion of the universe. That 21-centimeter light has been stretched, its wavelength elongated by a factor of 10 or more as space itself has expanded. This shifts the signal down into the low-frequency radio band, a part of the spectrum that is incredibly difficult to observe from Earth's surface. Our own atmosphere is murky at these frequencies, and human-made radio interference from everything from television broadcasts to satellite communications creates a deafening roar that drowns out the cosmic whisper. But even if we launch our telescopes above the atmosphere, we face an even more confounding problem. The galactic foreground, our own Milky Way galaxy, is a brilliant source of radio waves, shining millions of times brighter than the signal we are trying to detect. This foreground noise is not a uniform hiss. It is a complex, swirling tapestry of emission from countless stars and nebulae. Separating the faint, uniform hum of the ancient hydrogen from the brilliant, structured glare of our own galaxy is like trying to hear a single, specific cricket chirping in the middle of a roaring heavy metal concert. It requires not just sensitive equipment, but algorithms of breathtaking sophistication to model and subtract every last bit of this local interference, hoping to reveal the pristine cosmic signal beneath. The quest to detect the 21-centimeter line is one of the grandest technological challenges in all of modern science, a high-stakes treasure hunt for the most important home movie the universe has ever made. If we succeed, we will not just solve the mystery of how reionization unfolded, we will witness it, but that faint cosmic whisper from the ancient hydrogen has already delivered a shock that still rattles the world of cosmology. In 2018, a small, ground-based radio experiment named EDGES announced it had detected something impossible, a signal from the cosmic dawn that was far deeper and more dramatic than any model had predicted. The EDGES instrument was designed to listen for the broad, global hum of the 21-centimeter line, not to make a map, but to capture the average signal across the entire sky. What it found was an absorption trough twice as deep as anyone thought possible. This was the universe's first starlight, casting a shadow far darker than anticipated. For the hydrogen gas to absorb the background radio light so strongly, it had to be incredibly cold, much colder than our standard models of the early universe can explain. Think of it like stepping outside on a sunny day and finding your shadow is pitch black and stretches for miles, defying the normal behavior of light. This is the level of anomaly the EDGES result represents. If this signal is real and not some bizarre artifact of the instrument or a subtle effect from our own galaxy, then our entire understanding of the cosmic dawn's physics is fundamentally wrong. We are missing a powerful cooling mechanism that chilled the primordial hydrogen gas to depths we cannot account for. One of the most radical, yet compelling, explanations involves that invisible actor, dark matter. Theorists have proposed that in the very early universe, normal hydrogen atoms could have interacted with dark matter particles in a revolutionary way. If these two components collided, the dark matter, which is inherently much colder, could have acted as a cosmic heat sink, siphoning thermal energy away from the hydrogen gas and dropping its temperature to the frigid levels needed to create the deep edges absorption. This would mean that dark matter is not entirely dark in its behavior. It can exchange energy with normal matter through some unknown force. Another, even more exotic, idea suggests that the radiation background itself was much hotter than we thought, perhaps warmed by the decay of other theoretical particles. A colder gas absorbing against a hotter background would also produce a deeper signal. Both of these solutions require physics beyond the standard model, the established rulebook for particle physics and cosmology. The EDGE's result remains hotly contested. Other teams have tried and failed to confirm it, and the monumental challenge of separating this signal from the galactic foreground means many are skeptical. The experiment itself was stunningly simple, a table-sized antenna in the remote Australian outback, and its claim is so extraordinary that it demands extraordinary evidence. The fate of this mystery now rests with newer, more powerful observatories that are scanning the same radio skies, searching for that same impossible shadow. The EDGE's anomaly is a stark reminder that the universe's first chapters may be written in a language we are only just beginning to decipher, hinting at a cosmic drama involving forces we have not yet named. Every mystery we have explored so far crashes against the same hard wall, the fundamental limitations of our own vision. We are cosmic detectives trying to solve a 13-billion-year-old crime, but our most powerful tools can only see the faintest outlines of the evidence. Even our greatest observatories, like the Hubble and Spitzer space telescopes, operate at the very edge of their capabilities when staring back this far. They have given us breathtaking deep field images, revealing thousands of ancient galaxies as faint, blurry smudges of red light, but these are the cosmic success stories, the relatively bright and mature galaxies that existed toward the end of the Reionization era. The very first generations of galaxies, the true pioneers of light, are simply too faint, and their light is too stretched for these telescopes to see. It is like trying to read the fine print of a historical document by candlelight. You can make out the general shape of the letters, but the specific words remain a frustrating blur. The light from these earliest objects has been stretched by the universe's expansion into the infrared part of the spectrum, a domain where Hubble's vision begins to fail. Spitzer was designed for infrared light, but it lacked the sheer resolution and light-gathering power to isolate these incredibly distant, tiny specks from the background glow of the cosmos. We are left with profound questions and only partial answers, inferring the existence of an entire army from the footprints of just a few soldiers. This is precisely why the James Webb Space Telescope was built. It is not merely an upgrade, it is a completely new kind of eye on the universe, engineered specifically to peer into this cosmic dark age. With its colossal gold-coated mirror and suite of exquisitely sensitive infrared instruments, Webb is designed to do what Hubble could not: capture the light of those very first galaxies directly. It is the difference between hearing a faint, muffled echo from a distant valley and suddenly being given a powerful microphone and amplifier that lets you hear the individual voices in the choir. Webb is looking for the starlight that finally ended the universe's dark ages, aiming to catch these infant galaxies in the act of blowing away their own gaseous cocoons and flooding intergalactic space with ionizing radiation. Every new, faint galaxy it discovers from this epoch is another crucial data point, another piece of the puzzle that could finally tell us whether it was the brilliant few or the dim multitude that lit up the cosmos. The answers are out there, hidden in the infrared whispers of the first dawn, waiting for the one telescope built to listen, The James Webb Space Telescope is our generational leap into the cosmic dark age. Its mission is to transform those faint, blurry smudges from Hubble's deep fields into detailed portraits of the very first star systems. This is not just about finding more galaxies. It is about studying their anatomy with a precision we have never before possessed. Webb's enormous mirror, coated in gold to better capture infrared light, acts as a colossal light bucket, gathering the incredibly faint photons that have been traveling for over 13 billion years. Its suite of instruments can then break that ancient light apart into a spectrum, a unique barcode that reveals the galaxy's secrets. From this barcode, we can rate its temperature, its chemical composition, its age, and even the velocity of its gas. We'll be able to see, for the first time, if these infant galaxies are surrounded by the telltale signatures of escaping ultraviolet radiation, the direct evidence that they were actively ionizing their surroundings. Imagine being able to point to a specific galaxy and say, with confidence, that this one right here was a fountain of ionizing photons, actively clearing the cosmic fog. Webb is designed to do exactly that. It will hunt for the specific spectral lines that act as a fingerprint for this escaping light, finally allowing us to measure that elusive escape fraction directly. No longer will it be a theoretical number. It will be a measurable property for thousands of individual galaxies across cosmic time. This data will settle the long-standing debate over what truly ended the Dark Ages, whether it was the collective effort of countless small galaxies or the concentrated power of rare, brilliant behemoths. The telescope's deep field observations will provide a definitive census, counting galaxies so faint they were previously invisible, telling us if we have been missing a vast population of cosmic contributors. Webb is not just observing the aftermath of reionization, it is watching the process in action, giving us a front row seat to the most important transformation in the history of our universe. Yet for all the power of our newest telescopes, the most vital clues might not lie at the edge of the observable universe, but right here in our own celestial neighborhood. Scattered around the Milky Way are ancient dwarf galaxies, cosmic fossils that have survived virtually unchanged for billions of years. These tiny, faint systems are not the brilliant pioneers of the early cosmos, but rather their direct descendants, frozen in time. They are the living relics of the Reionization era, offering us a unique window into the past if we want to understand the small, faint galaxies that likely did the heavy lifting of ionization. We cannot just look for their distant, faded light. We can study their modern-day counterparts up close. The theory is both simple and profound. The dwarf galaxies orbiting our Milky Way are thought to be largely pristine, having formed most of their stars in a furious burst during the universe's first few billion years, and then entering a state of suspended animation. They are cosmic time capsules. By dissecting them, we can learn about the properties of the countless similar galaxies that existed during reionization. What kind of stars did they contain? How were those stars arranged? And most critically, how easily could their radiation escape? We can measure the chemical makeup of their stars, which tells us about their age and the ferocity of their earliest star formation. A dwarf galaxy with very few heavy elements is a sign of a system that has been dormant since its initial burst, a perfect analog for the galaxies that flooded the early universe with light. We can also study their structure. Many of these local dwarfs are incredibly diffuse, with stars spread out over vast volumes. This low density might have been the key to reionization. In a sparse galaxy, ultraviolet radiation from massive stars would have had a much clearer path to escape, encountering less obstructive gas and dust on its way out. A dense, compact galaxy might trap its own light, but a wispy, extended one could have been a perfectly efficient ionizing engine. This turns our search inward, from the cosmic horizon to our own galactic halo. Each of these faint, orbiting specks is a piece of the puzzle, a preserved example of the very workhorses that transformed the cosmos. They remind us that the answer to one of the universe's greatest mysteries might be hiding in plain sight, quietly circling our own starry city, waiting to tell their story. The universe was not illuminated with the flip of a single cosmic switch. The final victory of light over darkness was a chaotic, fragmented affair, a slow percolation of brilliance through a stubbornly dark cosmos. This was the era of the bubble universe, a time when space was a patchwork quilt of ionized clarity and neutral shadow. The central mystery is not just that these bubbles existed, but what their specific shape and size can tell us about the forces that created them. Each bubble was a sphere of influence, a region where a source, or a cluster of sources, had managed to burn away the local hydrogen fog. Their growth was a relentless push against the neutral medium, a battle fought at the speed of light. But were these bubbles small and numerous, like the effervescent fizz in a glass of soda, or were they vast and sprawling, like great celestial caverns carved by a few brilliant behemoths? The answer is written in their morphology. A universe dominated by countless small, faint galaxies would have produced a fine, frothy texture, with millions of tiny bubbles slowly growing and merging. In contrast, a cosmos powered by rare, monstrous quasars would have featured a few enormous, rapidly expanding spheres, their boundaries sharp and defined by the quasar's intense, focused radiation. The way these bubbles eventually connected, forming ionized tunnels through the cosmic web, holds the key to the entire process. Did the filaments of dark matter that form the universe's backbone guide the growth, with bubbles forming first at the dense intersections of the web? Or did the radiation flood the vast, empty voids first, leaving the denser knots of gas for last? Mapping this ancient patchwork would give us a direct image of the reionization workforce in action. It transforms the mystery from an abstract question about energy into a tangible, structural puzzle. The ghostly imprint of these bubbles is still etched into the distribution of galaxies we see today, a frozen moment from the epoch when our transparent universe was stitched together, one brilliant patch at a time. The first stars did not just bring light, they brought a kind of cosmic poison. When those colossal population 3 stars reached the end of their brief, furious lives, they did not fade quietly. They exploded in cataclysmic supernovae that fundamentally changed the recipe of the universe, seeding the pristine cosmic gas with the first heavy elements, what astronomers call metals. This was the original pollution event, and it altered the course of cosmic history. Before these supernovae, the universe was a pure, simple place, composed almost entirely of hydrogen and helium. This purity was the secret to the incredible size and power of the first stars. Without heavier elements, the primordial gas could not cool down efficiently. To collapse and form a star, the gas had to become incredibly dense and hot, a process that naturally favored the birth of true behemoths, stars hundreds of times more massive than our Sun. These giants were perfect ionizing engines, blazing with intense ultraviolet light, but their death throes scattered newly forged elements like carbon, oxygen, and iron across their surroundings, and this contamination had a profound consequence. It acted as a cosmic coolant. These metal atoms are far more efficient at radiating heat away than simple hydrogen or helium. Now, when a cloud of gas began to collapse, these metallic impurities allowed it to shed its heat much more effectively. The cloud could fragment into smaller, denser clumps. This is why later generations of stars, including our own Sun, are so much smaller and more numerous. The universe went from producing a few brilliant giants to spawning countless smaller, cooler stars. And here lies the critical mystery for reionization. How did this shift in the stellar population affect the great cosmic thaw? A single, massive population 3-star was a ferociously efficient ultraviolet factory. Its hotter surface blazed with the high-energy photons needed to rip electrons from hydrogen, but a cluster of smaller, sun-like stars, born from metal-enriched gas, would produce a much tamer, cooler light for the same total mass. They were less effective at the specific task of ionization, so, as the universe became progressively more polluted with metals, did the very process of star formation become less efficient at driving reionization. The pollution that allowed for more stars to form may have also made each star individually weaker in the cosmic battle against the neutral fog. This creates a paradoxical feedback loop. The first stars, through their spectacular deaths, created the conditions for more stable, long-lived galaxies to form, but they may have also sowed the seeds for their own obsolescence, gradually replacing the brilliant ionizing titans with a dimmer, more numerous population. The entire pace and conclusion of the reionization era might have been dictated by this gradual enrichment, a slow poisoning of the primordial well from which all stars are born. The cosmic web was the invisible blueprint upon which the first light was drawn. This vast, filamentary architecture of dark matter, stretching across the emptiness like a cosmic nervous system, did not merely host the reionization process, it actively directed it. The great mystery is whether the clearing of the cosmic fog began in the bustling intersections of this web or in the quiet, empty deserts between them. Imagine the universe as a colossal, three-dimensional spiderweb still shrouded in morning dew. The dense knots where the silk overlaps represent the future homes of galaxy clusters, while the long, connecting strands are the filaments, and the giant gaps between the strands are the cosmic voids. When the first stars and galaxies ignited, they did not appear at random. They were born along this pre-existing dark matter scaffold, with the brightest objects forming at the nodes and smaller galaxies lining the filaments. So, where did the ionizing radiation go first? One compelling theory suggests the process was top-down. The most massive and luminous sources, the early quasars and big galaxies at the web's nodes, would have lit up first. Their intense radiation could have blasted outward, carving the initial bubbles of ionized gas. From these powerful hubs, the ionization would then have streamed along the filaments, following the paths of densest gas, like water flowing through a network of canals. The voids, being nearly empty, would have offered little resistance and were likely ionized last, almost as an afterthought. But a competing idea proposes a bottom-up approach. Perhaps the radiation from countless small galaxies embedded within the filaments themselves created the first overlapping bubbles. These bubbles then grew and merged, their edges meeting at the nodes, effectively squeezing out the last remnants of neutral gas from the universe's busiest intersections. The voids, in this scenario, might have been cleared early, precisely because there was so little gas there to ionize. The answer to this directional puzzle is written into the fossil record of the reionization era. If the nodes were cleared first, it would imply a universe dominated by a few brilliant titans. If the filaments were the pioneers, it points to a collective effort from a vast population of smaller galaxies. The very architecture of the cosmos, it seems, held a casting call for the leading roles in its own transformation, and how that casting unfolded determined the pace and pattern of the universe's greatest dawn. This search for the cosmic workforce forces us to consider a truly radical possibility. What if we have been looking in the wrong place entirely? The standard story points to stars and quasars, but a handful of scientists are chasing shadows, proposing that the true architects of reionization were not astrophysical objects at all, but the very fabric of the cosmos decaying around us. These are the alternative theories, and they challenge everything we think we know about the universe's first light. One of the most profound ideas involves exotic, theoretical particles left over from the Big Bang. Imagine a universe filled with an unseen sea of these particles, each one a tiny, unstable relic from the first moments of time. Now, imagine these particles slowly, inevitably decaying. With each decay, they would release a burst of energy, a faint whisper of radiation that would permeate all of space. This would not be a brilliant flash from a single point, but a universal, gentle glow, a background hum of ionization that could have persistently warmed the hydrogen gas for millions of years. This energy would not have reionized the universe on its own, but it could have been the crucial priming agent, subtly heating the gas and making it far easier for the first starlight to finish the job. Another, even more dramatic proposal involves the annihilation of dark matter. We already considered the possibility of dark matter particles colliding and vanishing. But what if certain types of dark matter were not just annihilating in rare events, but were designed to do so in a great final cataclysm? A specific class of theoretical models suggests that in the early universe, dark matter could have been poised on a knife's edge, stable until a critical moment triggered a chain reaction of annihilation. This would have released a staggering wave of energy, a cosmic firestorm born from the invisible universe itself, potentially flooding the cosmos with enough radiation to reionize it in one fell swoop. These ideas are, for now, firmly in the realm of speculation. There is no direct evidence for such exotic particles or for self-annihilating dark matter. They are mathematical possibilities, born from the desire to explain anomalies like the impossibly deep edges signal or to solve the nagging energy budget problem. Yet, their allure is undeniable. They suggest that the story of cosmic reionization might be a tale of two universes, the visible and the hidden, working in a strange and violent partnership. They force us to ask whether the stars and galaxies we see are merely the supporting cast in a much grander cosmic drama, one whose lead actor remains completely invisible to our telescopes. This incredible uncertainty, this battle between the standard and the speculative, brings us to the final and perhaps greatest mystery of all. After all this searching, with all our powerful telescopes and brilliant theories, how close are we to actually knowing what happened? The brilliant engines that lit up the cosmos did not shine forever. Their ultimate fate is the final, poignant mystery, a question that ties the birth of our universe directly to the galaxies we see today. What became of those first stars and galaxies after they flooded the universe with light? The most massive of the population, 3 stars, lived fast and died young. Their deaths were not quiet fade-outs, but titanic supernova explosions of a scale we can scarcely comprehend. These blasts were so powerful they would have utterly obliterated the star, leaving behind no dense core, but instead scattering their enriched guts across vast tracts of space. This stellar ash became the raw material for the second generation of stars, seeding the cosmos with the heavy elements that would eventually form planets and life. But not all of the first stars were destined for complete self-destruction. Slightly less massive giants might have collapsed directly into black holes, vanishing from the visible universe and leaving behind only their gravitational pull. These primordial black holes, if they exist, could still be drifting through the Milky Way today, ancient relics of the cosmic dawn hiding in plain sight. And what of the first galaxies, the nurseries that cradled these early stars? They did not simply vanish. They began a long and violent journey of cosmic evolution. Through countless mergers and collisions over billions of years, they were cannibalized, their stars and gas assimilated into larger and larger structures. The brilliant, clumpy proto-galaxies that drove reionization are likely gone, but their stellar populations live on. The oldest, most metal-poor stars in our own Milky Way's halo are the direct descendants of that first generation, refugees from those long-vanished infant galaxies. Our galactic home is, in part, a museum built from the ruins of the first cosmic empires. This means the very objects that ended the universe's dark age are not entirely lost to time. Their remnants are woven into the fabric of modern galaxies, and their final black holes may lurk at the centers of giant ellipticals and spirals, having grown over eons into the supermassive beasts we observe as quasars. The story of reionization did not end when the last neutral atom was ionized. It set in motion the chain of events that led to us. We are here because those first stars lived, died, and lit the way. These 25 mysteries, from the very first spark to the final ionized photon, form the greatest unsolved epic in cosmology. We have journeyed through the enigma of the first light and the contentious timeline of the cosmic dawn. We have questioned whether it was an army of faint galaxies or a few brilliant quasars that did the heavy lifting, and we have wrestled with the frustrating unknown of the escape fraction. We have explored the clumpiness of the primordial hydrogen, the missing satellite problem, and the thermal history of the intergalactic medium. We have decoded the Lyman-alpha forest and debated the era's dramatic conclusion. We have considered the whispers from dark matter, the potential of dark galaxies, and the forgotten second act of helium reionization. We have seen how feedback loops govern the process, distinguished the cosmic dawn from the Epoch of Reionization, and embarked on the monumental hunt for the 21-centimeter line. We have been shocked by the Edge's anomaly and have placed our hopes in the James Webb Space Telescope and the local fossils of dwarf galaxies. We have mapped the bubble universe, understood the poisoning effect of the first metals, and traced the influence of the cosmic web, all while daring to consider radical alternative theories and pondering the ultimate fate of the very first stars. This is not a closed book, but a living, breathing frontier of science. We are in a golden age of discovery, where new telescopes and technologies are peeling back the layers of time, bringing us closer than ever to witnessing the universe's own origin story. The answers are out there, waiting for the next curious mind to find them. What cosmic mystery captivates you the most? Share your thoughts in the comments below, and subscribe to join us as we continue to unravel the universe's deepest secrets.